Several authors predict that alpha particle structures could be present in atomic nuclei. There are convincing arguments of such structures. Of course, there is still, let's say, difficulties, or maybe some persons who are not considering that this is not the case, but we see everywhere alpha particles. I think in my calculation, as well as in some experiments, we see alpha particles, so probably this is true. So I based my work on alpha particles, and also on some other substructures of alpha particles, which are NNP, this is tritium, NPP, which is helium-3, and also NP, deuterium, etc., NN. So you can see here, you can see here that the binding energy values of deuterium, tritium, helium-3, and NN are related through that very simple equation. I will then explain why. For more details, of course, of my theory, it's necessary to rely on my former presentations or to what is on internet, of course, on the same subject. What is important is to say that according to my hypothesis, it's an hypothesis, of course, it's my theory. The binding energy of every nucleus is the sum of the binding energy of the different substructures and the binding energy among these substructures. Of course, this deserves some discussions, because this is an assumption on my side, but it's based also on hundreds of calculations for nuclei I have made and which show this possibility. So I have some arguments to present to persons, and I wish to discuss that with others, mainly with you. The day before I was decided that I will present my theory in infinite energy. I agreed that with George Eggerly, our friend George Eggerly, and maybe one time we will discuss it. I know that a lot of people here in this room have similar ideas, so this is very interesting. And especially Bill is there. Bill is also a strong supporter of these kind of ideas. So I will present today the examples of palladium and silver. Why? Because they have the same number of alpha particles. It is a fact that the odd number of Z have the same alpha particle than the others. Of course, palladium is 46 and silver 47, but the alpha particles are the same. It's the reason why I present them always by pair. So these are the values I am using. I am using some types of lines which facilitate my calculation. These lines disappeared in the final calculation because I convert everything in deuterium, tritium, and helium-3, and also NN, which are known particles. So this is important to know. I do calculations, but afterwards I take again what is known. I have some examples very quickly. For instance, the most important one, according to me, is oxygen 16. This is 4 alpha particles and a certain number of lines. This is, after my hypothesis of calculation, 2NN plus 2NP, which is 4A, because as they are mostly NN plus NP, I have merged them in A to A's. You see that my calculation come very, very close to the experimental value. We have 3 keV difference. And it's the same for all of others. The differences are about not more than 20 kevs. For the whole, this means that for each nucleus, if if each nucleon, if you divide it by the nucleon, it's 0.1 keV. It's not very important. We have here other comparisons, gallium 69 and 71. They differ by 2 neutrons, and we can see that this is just a rapid calculation of the binding energies of the experimental ones, that the difference is equal to 2 tritium binding energies. The same for iron here. It is 3 neutron more, and the difference is 3 binding energy of tritium. These are easy ones. Of course, the others are a little bit more complicated. Sometimes it's, you will see a combination between tritium and helium-3, or combination with Nn plus Np, etc. So these I will show. These are the easy ones, just to give an idea of the system. This remark I already did, so we can come to the comparison between palladium and silver nucleides. So we have here under all the summary of the binding energy distribution of these nucleides. I begin with palladium 98 and 99. You can see that these differ by 1 neutron. And what differs if 1 neutron is introduced to 98, it becomes 99, of course, mathematically. What changed is this. 17 becomes 18, 25 becomes 24. And what changed also is this. Actually, there is 1 neutron more. It is bound by Nn plus Np. It's the reason why there is 1 more. But there is a second more because there is modifications of these ones. Half NNP plus half NPP became 1 NN plus 1 NP. Consequently, of course, there is 0 NNP here and 2.5 only. This is very important and is the backbone of the theory. The basic rule, actually, I have put it here, for the core is to have, for, of course, palladium and silver, to have 21 NN plus 21 NP. This is 42A. I explain later, if I have time, why. And this changes, of course, with the nuclei. For the supplementary neutrons, this does not change. The basic line is Nn plus Np per neutron. And for the proton, NPP. That's all. And so this is the reason why you can see here lines which mark the difference with the basic rule. When the difference is too important with the basic rules, the nucleus is not stable. Especially when there is here a minus, this means that the core of this nucleus is not stable. You will see it in the following. Here we have palladium 100 and 101. So we can see that these have the same number of Nn plus Np, but still it's not enough to be stable. There should be 21, 21. You can see that there is, of course, 1 neutron more in palladium 101 compared to 100. That's normal. You can see that here also 1 neutron is bound with 1 NPP instead of 1 NN and 1 NP. There is a decrease of 1 here, an increase of 1 and even 2 because the second neutron which entered is bound directly by NPP. So we can see that the only difference between these two nuclei is here. It's not much. Same now for 102 and 103. Palladium 103 is stable. It's the first one which is stable or considered as stable. Because there is an equilibrium between 21 and 21 here. Of course, there is also a little discrepancy between NN and NP, but this is not very important. It makes this nuclide stable, even if it's not very important. The natural abundance is 1%. Of course, those who are better structured have a natural occurrence abundance which is bigger, of course, that's normal. Now we have PD 103. You can see that this one, compared to Palladium 102, is not stable because he has 1 NP more than NN. But the supplementary neutron-proton system is quite good. So now let's take silver 103. Silver 103 is decaying beta plus and EC to be palladium 103. You can see here that 1 NP is becoming 1 NN compared here. There's a change. And a change also at the structure of the neutron and proton supplementary. 2 NN plus 2 NP are becoming NPP, as well as 1/2 NNP. So at the end, this modification, transmutation, has as result to change 1 NP in 1 NN here, and a little bit here. PD 104, etc. You will see that it's the same. This is PD 104 is stable, 21-21, and the structure of neutron-proton supplementary is also stable. Silver 104 is decaying beta plus into palladium 104, and this makes, of course, that 1/2 NP are becoming 1/2 NN. Also, there are changes here. Instead of having 7/2 NN, 7/2 NP, you have only 5. 2/2 became NPP, etc. Taking 105 and palladium and silver, you can see the same phenomenon. 105 palladium is stable. Silver is not stable. There is a difference of 1 NP. And you can see here, what is interesting, that the structure of NNP is practically the same. Let's say there is a difference of 1 NNP and 1 NPP. There is a decrease, or an increase if you want, of NNP and the same comparatively of NPP. So this is the difference between these two nuclei, according to my theory always, of course. 106, AD is stable, 21-21, and we have this structure. Silver 106 is decaying in palladium 106, so there's a little change. 1/2 NP becomes 1/2 NN, and there's also a change, consequently, in the way the neutron and proton are bound to the core. You see, 5 NN and 5 NP became NNP, and also 1/2 NNP. So there is a change here. Palladium 107 and silver 107 are interesting because now, instead of having beta plus and EC modifications, we have beta minus. Why? Because we arrive at the possibility, there is enough energy to have 21 NN and 21 NP here. But for palladium, there begins to be too many neutrons which are in the not in the core. Of course, the lifetime or the half-life of Palladium-107 is quite important, but it decays into silver. And look at the modifications. There is no modification in the core. Every one has 21. Here, there is 1 NNP of palladium, which became NPP in silver. That's all the difference. And the calculation, frankly speaking, is about a few kevs difference compared to the experimental value. So I can say, after having calculated hundreds of these nuclides, that there is really a phenomenon. So we have palladium now 108, which is stable, 21, 21. Palladium, and then silver 108. Silver is still decaying beta plus. There's 22 against 20. This becomes 21, 21. And you can see that at the level of the neutron and proton supplementary, there is no difference. It's just a little change here, which makes silver palladium. But silver, it's the reason why we have 108 bis. Silver is also decaying mainly beta minus in cadmium. So instead of having 23 alpha, we have now 24 alphas. Because cadmium is 48, so they have 24 alphas after mass theory. Of course, consequently, there are 22 and 22 here, N and P, because there are more. And little differences here, mainly what concerns NPP. Why? Because here we have only 12 neutrons left outside the core, and here we had 15 neutrons outside the core plus 1 proton, because these neutron protons served to create the alpha particle. So we have also palladium 109 and silver 109. As we know, palladium 109 is decaying beta minus into silver. Still, we have 21, 21 here, and we have some little differences. 1 NNP becomes 1 NPP. You can see here the difference. And also 2 NN and 2 NP become 2 NPP. But this is the only difference between palladium and silver, always according to my theory. 110 palladium is the last one, which is stable in the series of palladium. And you can see here that there are two possibilities of breakdown for palladium. We have still 21, 21, this is normal. Here we have 10, 10, 6.5, 1.5. This is an excedent of lines of 16, 93, 75. The excedent here is the same, but the distribution is different. There are some flexibility. If the more neutron we have, or proton outside the core, the more flexibility we have in the modifications. I cannot develop it now because we have not the time to do that. But anyway, it's important. Silver, 110. We have still the same structure with the same N and neutron-proton structure, yes. So now we have only beta minus decays because there are enough energy. And so you can see that palladium 111 will decay in 111 silver, etc., etc. Because this is always being the same now till the end of the series. And you can see the little modifications. Here we have 4 NNP, 4 NP, which are modified in NPP plus 1 NNP. The same with palladium and silver 12, it's always the same kind of things. Here also, you have 21, 21 with some modifications at the level of the neutron and the proton supplementary. Sometimes very few, it's not very important, you see. 2 and 2 here became 2 NNP, that's all. Here it's half NN, half NP, which become half NNP, that's all. Here it's the same, and it's actually the end of the series. You can see, for instance, that silver 116 and silver 117 are differing only by 1 NPP. There is 1 neutron more, which is bound to the core by 1 tritium bound. That's all. Now we come to the core structures of palladium and silver. You can see here a schema, which is about, let's say, 23 alpha particles, which are bound by 42 A bounds, which is 21 NN plus 21 NP. This is always according to me, to my theory or my hypothesis, the core structure of the 2, palladium and silver, provided they are stable, of course. If they're not stable, there is less A bonds, but more NP bonds. This is an example of calculation. You see, I calculate the core, number of alphas, number of NNNP, and then the rest. And you can see the precision. The precision for palladium 108 is 4 keV compared to the experimental value. Here it's a bit more for silver, but silver has only a half-life of 24 seconds, so sometimes it could also be a little bit the verifications, the experimental verifications. They say, of course, that they're able to do as well when it is 24-second half-life than when it is stable, but okay, this is as it is. Huh? So, hypothesis of creation of 1 alpha particle. We have seen that silver can also decay in cadmium. So I do the following hypothesis within my own hypothesis. So it's a second hypothesis, of course, we have to discuss if we have time. If a deuteron merges with the structure of palladium 108, the result is silver 110. And silver 110 decays into cadmium 110. Or actually, there are 14 supplementary neutrons in cadmium 110. In silver, there are 17 neutrons and 1 proton, which serve, of course, to create the alpha particle. So the beta decay of silver 110 transforms 1 neutron into 1 proton. So 2 neutrons and 2 protons of silver 110 create a new particle. This we see, yeah, we'll be finished on time, no problem. You can see the difference here. 23 alpha, 24 alphas, 21, 21, 22, 22, and some differences here on the level of the neutron-proton supplementary. Of course, there are differences because here there are only 14 neutrons outside the core. Here there are 17 neutrons plus 1 proton. And these are the conclusions. So I can say the following. The breakdown of the binding energy of a nuclide is based on alpha particle bonds, after my theory, deuterium bonds, which is NP, tritium, helium-3, and also NN bonds, which is part of alpha bond. This is one point which on which I can conclude, still within a theory. Second, assumptions about the structures of the nuclei based on their similarities could be made. We can see that they are very similar. The core is very similar, and also the neutron and proton structure is also outside the core is also very similar. So really, it's an important point, I think, for my theory, but not only for my theory, but also for, let's say, our concern, which is cold fusion. So I say third point, usefulness for our research. This is a simple structure which allows to follow the transmutation process in an easy way and consequently determine the nuclear modifications each time a nucleon is added to a nucleus. So it allows to easily follow the transmutations yield in the frame of the condensed matter nuclear science. So thank you for your attention. I hope I was on time. I am ready. Yes, Mr. Cheshire. Professor Cheshire, or even Konrad, if you allow.
No problem. Could you come back to the second transparency? You have explained.
Just a moment.
The number of lines and so, and
yes, but you are new with that. The others are not asking me the questions about the lines.
Yeah, the second one. Oh,
because
here,
they are.
No, this is a comparison between
this.
lithium. This one. Yeah.
Yes, page 4. Yes.
The point is, the idea to calculate some clusters and compose the nuclei of clusters is okay. It works, of course, and we see that the results are really good compared to experiment. But the point is, first one, it is we are speaking about charge symmetry of nuclear forces. So neutron-proton interaction should be equal to neutron-neutron. Yeah. Only difference is the Coulomb interaction, okay? Yeah. And this is just the first point I wanted to mention, because the Coulomb interaction in nucleus is rather high. It makes maybe 20% of the total binding energy, of course, of the opposite sign. And if you take just the binding energies, neutron, proton, and neutron, neutron, you can, of course, a little bit include this Coulomb interaction. But the problem is that the Coulomb interaction is long-range interaction. So all protons interact to other protons within the nucleus. So it is something what is very surprising here if you compare the things. Another point is if you compare helium-3 and tritons, there is a large component of so-called three-nucleon interaction. This is just a very nice example that three-nucleon interaction, three-particle interaction in nuclear physics are very important. It makes also, let's say, 10% or even more. So it is something that maybe is already included, because you calculate, you count the number of three-nucleon systems there. And the third point, I'm sorry, I saw this. The third point is that at very heavy nuclei, we observe also carbon-12 decay. So this may be the idea to include also for heavy nuclei carbon-12 clusters or oxygen-16 clusters as well. Okay, of course the number of the clusters will be lower and the contribution will be also lower. This is just the idea. So, but it's very surprising that the results are so close to the experimental values. So it is something I cannot understand.
You cannot.
It is something what is very interesting. So once again, the problem is the Coulomb interaction. There's something you cannot include in such a way. I think you have proposed other contribution coming from the parity or pairing interaction or symmetry. Contribution, neutron-neutron and neutron-proton, as compared to the liquid drop model, because it works also very well. So, and the last point, there is magic nuclei, because they are bound much stronger compared to surrounding, and how you can include this difference between magic nuclei and the usual nuclei above.
Yes, thank you for the question. Of course, it's important because you are exactly doing the points which are controversial with, let's say, classical nuclear physics. I fully agree on that. Yeah, I fully agree on that, you say, first of all. Second, I can answer all these questions, perhaps not today, because it's a bit too long to explain everything. But I have a theory on internet on my hypothesis. My hypothesis, as I said the day before, or it was the day before yesterday, is the following: that I am working with symmetries between masses and antimasses, which is not accepted. I agree. But you can see the results. And these results are obtained very easily. Very easily. So I think, after having done hundreds of calculations of that kind, that my theory deserves some discussions. Of course, not here now in 5 minutes. But it's the reason why also we decided that I will write an article on our journal Infinite Energy. We can discuss, I hope, with all those who are interested. There are some points, and especially the magnetic dipole of the neutron and the proton, I have calculated on basis of mass and antimasses, which is very interesting and which is new and not accepted. I agree. But if you want, you could have a look at that. You can say that I am perhaps a bit mad, or you can say what you want. But after having calculated so many, and even the big ones, I have also on internet the calculation for uranium, and etc. So having calculated so many, I cannot say that I am totally wrong. Maybe there is a thing I have missed, or maybe there is a thing the normal theory, or the accepted theory, has missed. You see? And this is the reason why we should discuss it. Yeah, okay. Yeah, okay. Okay.
Well, this is going to be a very classical, in some ways, presentation. Not terribly controversial, but somewhat innovative. I'm attempting to model the atomic mass, which means the mass of the nucleus and the electrons, in terms of the number of neutrons and the number of protons, which is exactly what nature does. Why is there an interest in atomic masses to begin with? Well, we could measure them to about 9 significant figures, which is amazing. And it also means if we have a theory, we can have some very precise theories about it, and hopefully we can test them against our observations. And our astrophysicist colleagues would like to know the atomic masses of exotic nuclei, to model supernovae. In particular, they would like to know where the so-called neutron drip line is, because during a supernova explosion, there is an enormous flux of neutrons which saturate all possible isotopes until they can't accept any more neutrons because it would be endothermic to do so. It's absolutely impossible to experimentally measure these very highly radioactive nuclei, so it'd be very nice if we could calculate what their masses were and thereby predict the abundances of nuclei which then radioactively decay by beta decay down to the same masses which are stable. And that would be a very satisfactory explanation to really the abundance of all matter on this planet, in the solar system, not quite in the universe, because not necessarily all matter is made by supernovae, of course, but certainly our solar system was. So I want to start off with a definition of what do I mean by local and global relationships. And we can see this formula here, which says that the mass of one nuclide, given by a number of neutrons and a number of protons, is related to 3 of its neighbors. That's what I mean by a local relationship. And if this relationship was in fact true, we could then make a global relationship which just says that the mass of a nuclide would be a function of the number of neutrons and the function of the number of protons. This is actually quite a nice idea because it's absolutely symmetrical. It doesn't treat neutrons particularly any more different than protons. And the functions are going to be different. That's why I've used F and G here. And this incorporates in some way any electrostatic repulsion. So that would include the Coulomb effect you were mentioning, Conrad. Let's look at this as a practical example. Here I've taken a group of 4 isotopes, and if we were to look at the masses, the sum of the diagonals, this mass plus this mass minus this mass minus this mass, would be about 0. In fact, it comes out to 10 kilo electron volts. Though I have to say, this is completely artificial. This is purely a coincidence, and I don't recommend using this method, but it does illustrate the method in general, okay? So don't use this method. It's not particularly good, and I've deliberately chosen something which shows it off, but it's a coincidence. But let's go back in time to 1935 and the Weizsäcker mass formula, which has already been mentioned. It depends on the bulk volume because the nuclear strong force is short range, but there's a surface, so there's a negative contribution there. There's a Coulomb contribution. There's a symmetry contribution. And effectively, there are 2 odd-even effects for an even number of protons or an even number of neutrons. I will talk about an odd-even effect, which is not of this kind later on. But I just want to give you an introduction to the concept. The reason why we've got -1 to the power of n is this is a 2-valued function, which is either 1 or -1. That is what I mean by odd-even. The effect is either positive or negative to approximately the same degree. And we find empirically that we have to divide by the square root of the mass number, which is n plus z, mass number A. I've used the latest data for this latest model. This is the atomic mass evaluation of 2020, which was published earlier this year in March. It contains some 2,371 experimental values of atomic masses, and on average the RMS experimental error in the estimated error in measuring these masses is about 98 keV. Let's call it 100 keV, and we can compare the predictions with the experimental error of that order of magnitude. And for historical reasons, not entirely valid historical reasons, the data is restricted to number of neutrons equal or greater than the number of protons, and the number of protons should be greater than 6, and the number of neutrons greater than 10. We're not really very interested in the masses of very light nuclei anyway, so I don't think this is a major detraction. But a lot of the models historically could not estimate low-mass nuclei, and consequently it was a kind of fiddle factor to make their results look a little bit better. That's not the case anymore. We can estimate the masses of light nuclei very easily. The experimental errors are obviously estimated by the individual experiment groups who are doing the experiments, and their estimates sometimes are actually overly conservative because they don't want subsequent generations to show how to improve. So the errors may be overestimated. I mentioned 100 keV as the typical error, the RMS error, but if we ignored the outliers, we would probably find it comes down to about 13 keV. So the vast majority of measurements are very accurate indeed. In fact, we can measure atomic masses of stable isotopes to less than 1 electron volt. And to exclude the outliers, I've ignored any isotope which has a declared experimental error greater than 125 keV, which is about 100 isotopes are excluded in this way. Taking into account of the experimental errors, there's a statistical concept called the model error, which takes the RMS value and quadratically subtracts the experimental error. But again, because the errors are not normally distributed, this leads to completely artificial conclusions, so I don't use this approach. I use another approach to evaluate the quality of the error, and the standard literature just uses the RMS error, so I'm only going to talk about the RMS error today. What does the data actually look like? On the left-hand axis, we see this is the S2n, that is to say, the energy required to subtract 2 neutrons from an isotope as a function of the neutron number. And if we look right at the bottom, we have a negative energy, which means that the isotope spontaneously emits neutrons. And up at the top here, we need a massive 40 million electron volts to remove a neutron from some presumably rather proton-rich isotopes here. We can see that every so often there's a kind of discontinuity. This is a magic number of neutrons, so we've got 126 neutrons here, 82 here, 50 here, 28 somewhere, 28 here, I guess, 20 here, and 8. 2 is not really very visible. So this is experimental data. Oops. And I would say the model I'm going to present to you can duplicate this exactly. In other words, the error in the prediction is less than the width of one of these little dashed lines, okay? So it would make absolutely no difference to demonstrate the predictions. So it's very good at predicting known data. But if we were to extend down this region here, where we're approaching the neutron drip line, I think the method I'm going to propose has some defects. I'm not going to demonstrate what those defects are, but I'm not pretending that all predictions are perfect. So it's a common problem of all these models that we can predict known data. It's much more difficult to predict unknown data. Nevertheless, unless we try, we will never succeed. The software I use is a proprietary least squares regression program written in C with optimizations for sparse matrices. It's about 4,000 lines of code. It analyzes at least 100 different nuclear models, and probably historically, I organized another 100, but I just discarded them as being not particularly interesting. It's taken me well over 25 years to develop. And the physicists here will probably be a little bit upset that almost no account is taken of underlying physics. On the other hand, the approach is not entirely new, and although no nuclear theory is involved, there is some rationalization as to why it works. So there is some literature about this kind of approach. The kind of approach, the local relations I mentioned earlier, started off in the 60s when Garvey and Kelson used an IBM card reader as a computer, a really primitive piece of equipment, with about 4 kilobytes of code, and they used iterative techniques to solve the simultaneous equations. However, it gave a remarkably good prediction of atomic masses. And this strange pattern here is rather like the one I gave earlier. You add this atomic mass, you subtract this one, add this one, add this one, subtract this one, and the result is approximately 0. So from any one of those masses, you could from any 5 of those masses, you could calculate the 6th one. But of course, you need the local masses to begin with. And of course, the neutron drip line, we don't have them. So actually, it's not a very practical method. Nevertheless, for historical reasons, and because of its high accuracy, it should be cited. Garvey and Kelson themselves realized that a local relation of this kind can be made into a global formula as a function of protons, function of neutrons, and a function of mass number. I've tried this myself. It really is quite good, but it's not perfect. And we'll have a look a little bit later about what kind of errors we can expect. An extension of that last global formula is to add a 4th term here, where we have a kind of function of isospin, where the difference between the neutron excess, and we add a pairing term. And now the errors are coming down quite dramatically to 200 keV, which is not at all bad, and with 565 parameters. Why so many parameters? And the answer is all these functions are functions of integers. The number of protons is an integer. So in fact, we have a table of lookup values for each function, and then we get 565 parameters. So, can we do any better than this historical approach? Well, we could search for the optimal local relations by assigning to each neighbor of a potential unknown mass some coefficient, and then use regression to find what coefficient we ought these masses would depend on. And this is a very practical approach. The first one which came to mind was something like this. And one notices this is rather like an approximation to a second-order derivative, but given that we have 2 dimensions of protons and neutrons, it's a 4th-order differential equation. So the derivative of the mass with respect to number of protons squared or number of neutrons squared is approximately equal to 0. But the RMS error is fairly high, a bit higher than the local relation, but it is much more general, of course. So there we go. Now here, here we have an RMS error. Now it's coming down below 200 keV to 173, and this is the formula. 512 parameters, which is not too bad. Remember, we've got well over 2,000 isotopes to determine, so having 500 parameters is not such a bad effort. And, yes, sorry, I've overlooked something here. This is not the same as the relationship I gave before. We've got we're looking at the number of neutrons multiplied by a function and the number of protons multiplied by a function. Obviously, the number of parameters here is exactly the same as some function of the mass number, because the mass number is equal to the number of protons plus the number of neutrons. And this, so this formula has exactly the same number of parameters as before, but a much better error parameter, error result. Okay, I think I'll skip that. But we can do much better still. Going back to that technique of finding the appropriate local solution, the computer comes up with this formula. And what this means is we want to find the mass of this central nuclide here, and we could do it by subtracting this one, adding twice that one, subtracting this one, adding twice this one, and so on. And the total the total would be 0. But if we divide by 4, we get quite a nice error figure, and it's 82 kiloelectron volts. So we've made a dramatic improvement over other methods. And we can write the formula down now, but instead of having 0 on the right-hand side, we have an odd-even function, which is not a function of the number of neutrons or protons directly, but simply goes, simply the mass number. We could have used n-z here with exactly the same result. That's why I said the odd-even effect, which I'm going to present, is different from the one in the Weizsäcker formula. And we can get even more complicated. If you can imagine, oops, why does this not work anymore? If you can imagine rotating this, you could try this one, adding to a vertical one, and you take the average. And that's what the next slide shows. 71 keV now, it gets better all the time. And the computer confirms this is the best possible local mass relation on a 5 times 5 plane. Again, we have neutrons going this way and protons going this way. Well, I couldn't resist going to 6th order partial differential equations. I mean, this is obviously a good technique, but I have to say I have absolutely no real justification for this. It just happens to work. And the RMS error for the global formula is now down from 170 to 91, but with a horrible 800 parameters. But because many of these functions are in fact fairly smooth, we can eliminate quite a lot of the lookup values in the tables, and with reducing it to about 550 parameters, we're back down to 100 keV. Now remember, the experimental errors were 100 keV, so we've got very, very, very close to experiment. Okay, I think I've covered that. And I think I've covered that. And we're short of time, so we'll go ahead. So what do the errors actually look like? Here I'm comparing EXP4D, which is just the acronym for my model. I've got, as I say, hundreds of models. And I compare it against the latest 2020 database. We see the mass difference here against proton number this time, and it's pretty smooth over the entire spectrum of possible isotopes. We've got 2,300 different isotopes here. There are some outliers, and it may well be these are not errors in the model, or they are anomalies in nature which we haven't got enough data to cover theoretically. But the vast majority, as you can see, are within 100 keV this way and 100 keV the other way. The fact that there are so few errors here, or even at the low end, is simply an artifact of the fact that we have fewer experimental data there. So it's got. I would expect the model to be similar to what's the center of this chart for all data. By the way, these beautiful charts are generated by software which you can download, and if anyone's interested to do this kind of thing, I'll be happy to give the web address. So let's summarize for a moment the global models. The von Weizsäcker model produced about an error of 3,500 keV, and we're down to 90 or 100 for more recent models of the kind I've presented. Bao et al., a Chinese group, were using the Yannicka and Yannicka's model, and they made some very minor changes, but I don't think even 206 keV are very good. I presented actually exactly their model at ICCF 5 in Monte Carlo 25 years ago. But you know, if the formula is right, other people are going to find it independently, and the Chinese group obviously did. I don't think they read my paper. So the judgment of the scientific establishment is, I would say, the Garvey-Kelson local relations had a major role to play in testing experimental data, comparing observations with what one expects. The corresponding global equations corresponding to the Garvey-Kelson local relations were not very good. There were always too many parameters, not very much physics, and after 50 years, it is time to overhaul the system. But, as I started off saying earlier, what we're really interested in, or at least what the astrophysicists are interested in, is the so-called S1N, the separation factor for one neutron to see where the neutron drip line is. And if we could estimate it, it would be very helpful indeed. Conrad is saying that there's less interest there now, but it doesn't matter. Perhaps with a higher precision, we can resuscitate some interest. The formula, in terms of local formula, would be something rather like this, where the mass of 1, 0 is the mass of a neutron with no protons, and this is just the difference in mass of two neighbors. And that's the similar formula for the proton separation energy. This could be useful, for example, in a binary star where a small satellite star is feeding unburnt hydrogen onto the main star, and so you have a fast proton capture process. And I think, Conrad, you mentioned this as well the other day. Given enough parameters, you can claim almost anything. So it's important to try and cut down on parameters wherever possible. However, when I try and apply, for example, a Coulomb repulsive term, or a symmetry term, or a surface term, to the complete set of functions without the interpolation, then there's absolutely no improvement. In other words, all the physics is already encapsulated without us needing to know about it. So I'm quite satisfied this is a robust method. So here are some results of the so-called separation energies. And now the number of parameters has come down quite dramatically from 500 and something. And the reason for that is when you do the subtraction of the neighbors, an entire function disappears. Because, for example, a function of the number of protons, when you take away a neutron, it's exactly the same function in both, and consequently the number of parameters evaporates, disappears. It's even better for protons because the function which disappears is a function of the number of neutrons, and there are more neutrons, therefore more parameters disappear. I've done the same thing for alpha particles, but unfortunately there the functions don't disappear, but even so you've got quite a good error. And I've also done the calculation for a forced beta decay, and we get really quite good results, 131 keV, I think. And these are all fundamental reactions which people would like to know given atomic masses, but calculating it directly rather than subtracting to look up for values is even more accurate still. So basically we have 2 or 3 times, the method is 2 or 3 times more accurate than the best other competing model. It's sufficiently accurate for supernovae. It's very good for verifying new experimental measurements, and it can be adapted to calculating the usual proton alpha, beta reaction energies. Okay, I think that's a lot. Oh, I would just add one point, if I may, for Philip, and that is, in your model, for every nuclide, you have, of course, the number of protons, number of neutrons, and then you arbitrarily choose some integer coefficients for, and the result, that is the reason why your formula turns out to be more accurate than this. But if you don't know in advance what the structure is, and there's no way of telling because it's some exotic nucleus, yes, of course.
Yeah, well, basically you're right.
nevertheless, it's a bit more complicated to say. First of all, I calculate the number of alpha which should be in every nuclide, the number of neutron and proton, and then I apply my system of lines. When I apply my system of lines, I come to, let's say, approximately a difference with experimental values of a few MeVs. A few MeVs, it's much compared to your system, that's true. It's very much, but then I adapt it by hand, and this is a discussion we have for years now, and you're reproaching me that I am doing some little things by hand. That's true. I look which one is the best. Of course, and this, I agree, it's not absolutely the best thing to do. Nevertheless, I'm not the first one who is doing these kind of things, because I'm sure that one day we will find a better solution. But frankly speaking, if you look at my results with only the lines, you calculate in 1 minute with only a few parameters, with an accuracy of which is quite good ones, and afterwards you're looking for a bit fine tuning. Okay, but tell me who is a chemist and others who is not doing that. Tell me here. Huh? Okay. So it's true what you say. And it's true that your model is better in calculation, but as you say, it's only calculation. It does not correspond to any physical thing. What I do, it corresponds to alphas, it corresponds to neutrons bound by systems.
No, that is what you're trying to prove. It doesn't correspond. That's what you're proving.
Okay, but I prove it, I calculate it. I have calculated it. As of course Konrad said, it's not in line with the normal physics. But we are not in line with the normal physics here. Are we? Yeah, normal, it's a physics which is accepted.
It's a kind of averaging. Why not?
Yeah. Okay. Okay. I leave it here.
I am looking for physics behind your approach, because it's very interesting. It is also very important to reduce the uncertainties in the masses, of course, for astrophysics, for some other purposes, of course. My point is, first, you have a large competition, because there is a large program in the United States based on density functional theory. They calculate all the masses, and they got a lot of money from the Department of Energy. So it is a very nice method, and they, I would say, would come to 1 kilo or 2 kilo electrons down because of the masses. And not only masses, but also excited states. They can calculate many things. There are, of course, some free parameters as well. No problem. But I wanted to say something different. I think this plane 5 times 5, this correction weighting parameters you have used, has physical meaning. I think this is just correction because of pairing. So it is not necessary to use neighboring isotopes or nuclei, but just use effect 2 more nuclei compared. There is what is the fields just neighboring should be empty, and then you should use the next one. Okay, because of pairing. Pairing is very large correction in the masses. So there is not this one. I think the previous one is better. Or this one. No, yeah, this one is. I think this maybe explained physically. And the next point.
The two are identical in terms of mathematics.
Okay, so this is mathematics, but can be explained maybe physically. Okay, and because of pairing, yeah, because of nucleon-nucleon interaction.
With this formula, the pairing is already taken into account.
Yeah, but you have additional correction that maybe is needed.
Yes, it's this one
here. Okay, there is one point, and I didn't understand how you included this magic nuclei correction. This is my question.
Yes.
And the third point.
Okay, one point at a time, otherwise I
Okay.
can't.
Sorry.
The magic numbers, because this is a function of the number of protons, there's one value, or several values of that number of protons is a magic number, so it's taken into account. And all the formulae here are either a function of the number of neutrons or the number of protons. So it intrinsically takes into account magic numbers.
Okay, so we can stay here at this diagram, our presentation, and this was very nice to see once again. I wanted to comment this product numbers. No. You have this not. The point is you have used another correction, the product of the function depending on the nucleon number and times z.
Yes.
Oppositely, n
Yes.
times something. And this is something what is maybe also can be explained physically, because in the heavy nuclei you have nucleons have a quark structure and they interact. So we know that inside, in the center of nucleus, you have even delta resonances and you have pentax quarks or even such structures. And that is something that maybe can be included just calculating this product functions, okay? So something I am looking for physical interpretation for
yes.
that, okay? Okay,
thank you.
It was very long, but...
I'm sorry, but I speak Italian. Allora, i salti energetici, in quale punti, cioè quei salti energetici che ci sono?
Quali?
I salti energetici, cioè
Stati.
vedo gli stati energetici lì, ci sono delle linee, corrispondono per caso di qua al polonio tra verde e viola e poi andando giù.
Okay. The colors correspond to different nuclear shells. It's just a convenience to see where one shell ends and the next one begins. And I mentioned this. There's a discontinuity here, for example.
Nickel rame? This orange.
This is going.
Nickel rame.
This is from oxygen going up to calcium, I would guess, from 8 to 20.
Perché no? È 29-30. E però arriva fino a 40, lo vede sotto? Quindi potrebbero essere isotopi anche nickel rame. Per di qua poi c'è pure il platino.
40 è un numero di neutroni.
Però va da 20 a 40.
Because there would be at this end a lot of neutrons.
Cioè c'è quello che volevo sapere, è se c'è una corrispondenza.
The lower we go down, the closer we get to emitting a neutron spontaneously. So we've got a lot of neutrons down here. So this might be I don't know, oxygen 30, for example, it would be something ridiculously charged with neutrons, okay?
Cioè non c'è una corrispondenza con le zone tipo nickel rame, platino, oro,
we can't see the elements here because I'm plotted against neutrons. But I could have plotted it against protons instead. It's just, this is prettier. Okay. Easier to see. Have you loaded your any presentation?
Plus invitation for our ICCF. I prepared this short presentation just during our Okay. So we are coming slowly to the end of our meeting. Oh, maybe I sit down. Okay. No, I can sit down. There's much better. Yeah, okay. Okay. So it was a very interesting meeting. I would say it was possible to discuss to the people personally after this one or even more time, 1 year separation, and we couldn't meet anybody, yeah, and only online meeting. This is not so nice, and we could have here very nice meetings, discussions, and so this is really very nice. I am very happy that we could do it, and just here in Italy, in this very nice surrounding, and so it is very special. And you know, Polish people like very much Italy. Okay, so this okay, not only Polish, of course, but you know, France and Italy, they are very close to each other. This, no, for Italy is something very special. Okay, so I would like to use the occasion to invite you. This is just an idea. This is not necessarily final thing that maybe we can discuss about it. Maybe not next or in 2 years, maybe in 5 years, if you want. We should meet all together in Szczecin, and therefore I prepared here a small presentation to show you where we can meet and why it can be interesting. Okay, so the suggestion is that we can organize ICCF conference in 2 years in Szczecin, 2023, because the next year will be organized in the United States, and the year after this we can organize something in Europe. Of course, I know there is some competition from other centers, but this is just my suggestion to think about it. And you see here University of Szczecin. There are 2 main buildings. One of that is a set of residence of the president of the university. It is not so large, but very nice building. And just on opposite side of this building, we are just to construct new building, completely new building, where our laboratories will have a lot of place. It is very close to the building here on the right hands. This the place of our Institute of Physics, very nice. And there is a parking place, and there, just in the front of this building, we hope we will have completely new building for our laboratories, for all the things. Okay, but this old building is very nice. There's of course not so nice as Assisi buildings and houses here, but the point is that Szczecin, it is a city that was built or expanded in the end of 19th century and begin 20th century. So it is a very special situation, because all the houses are made or built in the one style, secession style. It is a very rare situation that we have a large area of the buildings of the same style. Okay, and we are just in the center of the Szczecin, and there are a lot of plenty of restaurants, possibilities to nightclubs, and so, you know, Szczecin is a place there are 4 or 5 universities, different universities. Our university, there is technical university, medical university, maritime university, all the possible things. And the number of inhabitants, it is over 400,000. So it is not large city, not small city, but you have already all important things which are, you know, if you want to spend good time, this is something what we can, you can be sure that you can do it. And here's the position of the Szczecin on the map. So Szczecin is written just in German language. because my computer is in German, you know, so I have maps also in German. You see on the here on the right side is Poland and Germany, and Szczecin lies just very close to the border at the seaside. The seaside not necessarily very close. This maybe 100 kilometers aside from the seaside, but it is we will see. And what is important here that we have a large airport very close to Szczecin, 130 kilometers. So we can have very nice transportation from here to Szczecin, using shuttle buses, or you can use also trains, which are very frequently there, and some other possibilities. Even you can take a taxi. And Polish taxi is not so expensive, and it costs maybe 30 euro to go to Szczecin by a taxi. Okay, that is also a large advantage of this location, because the price level in Poland is maybe half of that in Italy or in Germany. Okay, so it is very nice situation. And then very much closer, once again, you see here Szczecin and seaside. The idea is, okay, you can travel by a ship, and starting from Szczecin to the very nice city, which is really very close to German border. This Świnoujście. It is also a very nice place that you can go to swimming, yeah, or other things. And we hope we can organize this conference during summer. And the point is that we will have a lot of support from the local government, but also from the Polish Physical Society, from central government, and so. So I have spoken already to some people, and they said, okay, this is possible. Yeah, so the idea is, the idea is also, that is also important for our project in, HME, it is important because we want to apply for the next project, and so so it is important maybe for that. And there are some photographs. There are some photographs of Szczecin. You see here the river going towards seaside, and there is maybe here on this old town, but it's of course completely different to the Italian old towns. This Renaissance buildings, but there are not so many because of Second World War, and Szczecin was destroyed because it was German city, and there were some bombardments during the war, and so. And here's an example of a new house. This is our Philharmonie, one of the best in Europe because of acoustic. Got some prizes, Europe prizes for new architecture and so, okay. And here's Świnoujście. So if you want to have a little bit pleasure, and so you see how many people are there, yeah. So, and but the nature is beautiful, you know. There's something you can take a bike and go away, and so it is something what we can do there. I think it is what we can discuss. Okay.
Okay. Thanks to Conrad, and thanks. You're welcome in Assisi, always. And then sit down for the lunch, because some people must take the flight and so on. Non è finito? Che c'è ancora? Ah, ok, excuse me, a moment, Mr. Collis. Excuse me, because there is a...
I'll try and be very quick. There's not much to show here, so we're not going to miss lunch. I think you already have vacated your rooms if you're leaving today. Ensure any debts are settled. Maybe there aren't any drinks in the fridges. I don't think we have fridges here, but there might be something. You might have a debt at the bar, for example. If you need an invoice or a certificate of attendance, you'd better email me at this address, and I'll do my best to send the documentation directly. And I was foreseeing the discussion of future meetings, and we need to discuss where the next workshop, not just where the ICCF 25 will be held. I think we all know that ICF 24 will be in California probably next summer, but a formal announcement has not been made. It will be chaired by Carl Page of the Anthropocene Institute, I believe. I suggested at the opening session that we think about some issues. Did anyone think about this at all? Does anyone want to discuss any of this? I'm not going to be offended if you say no. I'm sure you're all hungry. Yes.
Question 1, simple, quick, cheap. Question 2, no. Question 3, hard work. Question 4, talk.
So, for example, for question 4, would you like to see workshops every year on a semi-regular basis?
I really like what the Russians do. So right now, I think, in about 20 minutes, they have a meeting every week. And it runs on Zoom. And it normally has about, I would say, between 40 and 60 participants. And Zatelepin and Klimov are the moderators, and typically they will have between 1 and 4 presentations and questions, and they review all the conferences that are going on. They review all of the papers, which is very interesting, and they all get into the weeds with the papers, which is very interesting. And like I say, it's once a week.
How do they get enough material to fill up a weekly meeting?
As I said, they actually seriously review other people's work.
Okay.
They go through it almost like part of the experiment by part of the experiment, by comment, and they discuss what's rubbish and what isn't, and what deserves further discussion.
For example, both of us were being invited to make presentation at this
I'm going to present there next week if I couldn't present today. So.
Do you speak Russian?
No. But what I try to do is, if I can, I will have Russian subtitles streaming above my, so I have it auto-translating and
very
stuff.
good.
But they present a lot of things. For me, this is in Russian. It's really bad.
No, it doesn't need to be. You put your phone by the speaker and you put Google Translate with transcribe on, and you just watch the words come up. Yeah.
So when they talk to us, they talk English. But it's hard to take the point when they discuss interesting things.
But to be fair, if you have a question, they will attempt to put it in English, or at least Zatelepin does. Mm-hmm. So yeah, I'd be happy to host that. I have all the equipment, and I'd be happy to host it.
Well, I think it sounds like a good idea. Something certainly we should try. And not give up the first failed attempt.
Even if it's once a month, I think that would be a start. They don't do it during the holiday period, so they took a break over the summer because no one would turn up.
I think that means that everyone's getting hungry.
To discuss something. Okay, from my point of view, this is something, of course, very interesting to discuss new things, and this what we propose is a kind of journal club. Yeah, we discuss the papers that are new, and we can discuss about problems and so.
They sometimes discuss. In fact, the majority of it is some Soviet research that never been. I have slides in my the other 2/3 of my presentation.
Yeah, that's a very good idea. Yeah, but
undisclosed work, and in fact, what you're finding is, as open research are publishing things, they're forced to publish Soviet research. So I had some slides in my presentation.
okay. But this is something what we could do. For instance, within our collaboration, we organize seminars every 2 or 3 weeks. Yeah. And discuss different things, of course. Yeah, there's something. The point is how much progress you can reach in such a way. Yeah, you can learn something. Yeah, but not progress. There's not progress. The point is, I would like to say something about your points, and my impression is that we have a progress now. So we are going, for instance, within our project, not necessarily for electrolysis, which is difficult to interpret theoretically, experimentally as well. We are going towards gas loading experiment. Okay, I think it is something what is very much more useful and easier to interpret. And then combine these results with the accelerator experiments. It is something which is really promising, because we have some parameters that can be measured with an accelerator, yeah, and then see what is the result at room temperature experiments, let's say. So we want to understand what is most important thing for heat excess. Okay, of course, what is important also to measure nuclear products during the experiments at room temperature, but it's of course not easy. We want to explain why the gamma are not emitted, yeah, why some other things we cannot see, and this is just part of our project to understand the things. But the new one, I don't know, because I spoke so long in my presentation, and finally there were no questions. But my hope is that, for instance, if we look for electrons in experiments, it wasn't made before, yeah, because to measure electrons, detect electrons is not so easy. There is a continuous energy spectrum. It is what it means that we need coincidence measurements, okay, to say something, because of background of some other things. So this, I think, a promising way to improve our knowledge about low temperature, or I would say nuclear physics at extremely low energies. Not low, extremely low energies. And then this is okay. So we need this connection between standard nuclear physics and experimental results obtained at room temperature, generally. And this is what we should think about. We should go in this direction, I would say. Because this is just, there are the people that are most skeptical, you know, if you discuss, if you want to apply for new projects, for new things, you will meet some people, nuclear physicists mainly. They would say, but this process is not possible. So you should have an explanation why it could be possible. Not necessarily, the theory can be not correct, of course, but you should show that some possibilities are open. We should study it, yeah, but it's not necessarily in contradiction to the standard nuclear physics. Okay, and then it's okay. The people are open-minded and want to discuss. Okay, that's all I wanted to say. Thank you.
For the last time,
Just a few words to say thank you very much for all the organizers, you know. Congratulations.